Is now starting. All attendees are in listen-only mode.
Good morning, everybody. We'll just get started here shortly. We'll give them maybe another minute here for everybody to log in, and then we'll get going. Thank you. All right, let's get going. Good morning, everybody. My name is Glenn Maxim, Trade Alley Liaison. Today we're going to be doing CO2-based demand control ventilation, DCV. First, we'll go over program reminders, rebates, and then we'll hand it off to Ryan Hoger from TEC and go over the demand control ventilation. New Trade Ally website. We launched this in June, so now it's called tradeallycenter.com. Please use this one. Don't use the old one anymore. Like I said, launched it in June. We got new Trade Ally Learning Center to access. We got webinars, online courses, access to marketing material, print portal. It's got a ton of information, energy efficiency programs about all our programs, easy access to rebate application, custom dashboard with alerts and messages, a form for the contractor to sign up as a trade ally. So you can go right on there. If you're not a trade ally already, go in there and sign up right away. What we're going to add later this year, we're going to keep doing updates on this Trade Ally Center website. We're going to find a Trade Ally tool for customers. So that'll be a sign up you guys will sign up for if you want us to put your information on the website where our customers will also be using this website, and they can look for people to do certain projects for them. Then we also have the updated dashboard with the Trade Allies project information on there. Boiler tune-up season is soon. This is what is needed for a boiler tune-up rebate. I need a signed application. Definitely our team, like we've done the past 12 years, we can assist you with that always. I need a boiler tune-up checklist. We also need pre and post combustion readings. We have to show some kind of increase in efficiency, even if it's a 0.1, but we definitely need the pre and post combustion readings. The final invoice, if the rebate is going to the TA, we need it subtracted off the invoice. So if you're one of our partner trade allies or you're getting the rebates coming to you, we have to have a copy of the invoice that you send to your customer, and it has to show the deduction of our rebate on that invoice. Like I said, any questions, just get a hold of me. I'll get you with an energy advisor for that customer, and they will take care of most of this for you and help you out with everything, so you don't have to worry about all the paperwork. Application end of year, new dates this year. So previous years it was the end of the year. This year, all business and multifamily custom applications with all the documents are due December 1st. And for any of the prescriptive, all the business, commercial, industrial, small business, multifamily prescriptive and partner is due December 8th. So we need to have everything closed out by the end of the year. So we're going to have to try to get everything in by these dates. It would be greatly appreciated by our team. Future webinars, next month we will be talking about the boiler tune-up, since that's going to be hitting here pretty quick. We got boiler and rooftop unit furnace tune-ups submittal requirements. So we'll have one of our EAs going over that with you next month on September 27th. Then Thursday on October 26th, we're going to be talking about ERVs. We'll have Ryan Hoger back from TEC. That is a Thursday, so please make a note of that. It's not going to be a Wednesday. It'll be Thursday at 10 a.m. Due to scheduling conflicts. Training requests. If you've got any training requests, please get a hold of me. I'm always looking for, recommendations on webinars, trainings, new stuff, maybe new technology, something out there you see that saves energy that we can use. Please let me know. Who are you going to call? Me. So please call me with anything, projects, even if you're not sure it's in our territory or not, I can find out for you. If it is in our territory, I will link you up with an energy advisor and an energy engineer for that customer, and everything will run smooth. You guys worry about selling the project. We'll worry about the paperwork and help you get through everything. Now, I would like to hand it off to Ryan Hoger. Let me change presenter here. All right, Ryan, you should have control now.
All right. And you should now see my slides.
Yep, I do see them. Thank you, and I will leave you alone.
Awesome. All right, let me minimize this giant image of myself because that's annoying. All right, sweet. All right, welcome back, everybody. We did this topic a year or two ago, so this is kind of a refresher for some of you, but for most of you, probably not super familiar. We're doing demand-based ventilation and specifically CO2-based demand control ventilation. There are different types as well. There's also other types for like parking garages and kitchens and stuff like that. We're not working on that today. We're working with CO2, which means indoor occupied spaces. So classrooms, offices, retail, those kind of spaces. So before we explain how it works, let's just throw the money in front of your face. There are two places that you're going to get your rebate. You're going to get a rebate for doing this from your gas utility, so Peoples or North Shore, or if you happen to be out in Nicor, NIPSCO, whatever, they have similar stuff. But Peoples or North Shore, and then you'll also double dip that with your electrical rebate, so ComEd for most of you. So if you are in, say, Chicago, you have Peoples Gas and ComEd, you can do one thing and get a rebate from both entities. And obviously the gas savings, heating primarily, you're getting from the Peoples Gas side of the equation. And then the electrical savings, cooling primarily, as well as fan energy, you're getting from the ComEd half of the equation. So for the gas side of the equation, this is what that rebate looks like for commercial buildings. It's a little bit different than other rebates because really what you're being rebated, or you're being incentivized, I should say, is for the CO2 sensor and the labor to wire that up to the controller, and then whatever programming tweaks you need to make to your controller. So in this case, instead of being like a per boiler, per chiller, per rooftop type rebate, it's a per square foot rebate. Because one CO2 sensor may be covering a space that's 1,000 square feet, a different one may be covering one that's 3,500 square feet, and hence the energy savings will in fact be different for the exact same widget that you bought. So it's a per square foot rebate, so 5 cents per square foot. Doesn't sound like a lot, like 5 cents. What the hell kind of rebate is that? Well, you start multiplying it and it becomes pretty big dollar amounts, and it can in fact in many cases pay for the whole project. If it's a large open area with only a small number of sensors for a lot of square footage, it'll pay back pretty quickly. In regards to rules, there is a specific exclusion for this rebate. If you look at number 2, systems with reheat do not qualify. So you can't cool the air, pay to cool the air down basically, and then also reheat the air and still be eligible for a rebate on that. The reason for that, so that would be like constant volume reheat or VAV reheat system, right? You got one big rooftop, it's cooling the air, and then your perimeter zones at the VAV boxes have reheat coils. You can't get a rebate for those because in that case, there's almost no gas savings because those are cooling only systems by definition. They run cooling year round. So cutting back the amount of ventilation air coming in doesn't really save any heat. It saves tons of electricity, right? But it's not going to save anything on the heating side because there is no heating on those systems because they're cooling only. So systems with reheat, you don't qualify for. But everything else you do, rooftop units, air handlers, anything that's constant volume, with no reheat coils out at the zones you'll be able to qualify for. On the ComEd side, it is very similar but slightly different in order to confuse you. Instead of 5 cents per square foot, it's $40 per 1,000 square foot, which for you that are good with math, that is 4 cents per square foot. So you get 5 cents on the gas side and 4 cents on the electric side. So you could get 9 cents per square foot if you happen to have North Shore Gas and ComEd, or People's Gas and ComEd. And like I said, other areas, if you're not in those areas, also have similar type of rebates. There's always rebates on the electric side because you're either saving cooling energy or you're saving heating energy if it's a non-reheat system. So demand control ventilation, how does this work? I assume you guys can still hear me, Glenn. I got a little air thing that popped up, so hopefully I'm still good. If not, no.
Yeah, I can hear you. You're doing good.
Awesome. All right, so how's this going to work? So first we got to understand how we ventilate a building normally, and then we'll understand how we can adapt it to this scenario. But people's comfort, as you know, is more than just temperature. It's temperature, humidity, airflow, ventilation. All commercial buildings, I can't think of any place that doesn't have this, but all commercial buildings will have ventilation codes associated with them, meaning that you have to bring a certain amount of outside air in order to dilute down the pollutants of inside air. As you probably know, indoor air in almost everywhere in the country is worse quality than outdoor air, unless you live next to some kind of, weird plant or something. But outside air is better, so we want to bring outside air in to dilute down the pollutants of inside. But we don't want to bring 100% outside air in most cases, because that would be really expensive to heat it back up, cool it back down, filter it, etc., run the fan. So we want to bring in just the right amount, and usually we turn to the codes to figure out what that correct amount is. Most of those codes have remained virtually unchanged for the past 100 years. Pretty much works the same way. You go to a table, look up how much outside air you need per person or per square foot, multiply it out, set your outside intake damper for that, walk away. That's how we've been doing it for like 100 years. This kind of shows you historical ventilation rates. This particular chart is for office buildings, but you could do something similar for pretty much, every type of space. Ignore this giant pyramid because that's buildings that are so old. If you haven't updated your building in 100 years, that's pretty old. But most of what you guys working on had ventilation rates that were 10 or even 15 CFM per person. For a brief while, we were at 20. And then for the past 19 years, our code system is based on approximately 17 CFM per person. I say approximately because in 2004 for ASHRAE and 2006 for the international code, we switched from a per person calculation to a per person plus square foot. So it doesn't always work out to exactly 17. So if we take an example, this is some little random bank. Take an example and look at it. If we had 20 CFM per person on the building, and there's 25 people that the space was designed for, you would bring 500 CFM of ventilation air into that space. However, in actual real life, how often are 25 people there? So when less people are at the building, right, in this example, only 5, you would still be bringing in 500 CFM. And when this lady's counting money all by herself late at night, it's still 500 CFM you bring in. So you're over ventilating for the amount of people that are actually there, because you have to design the space for the worst case scenario, right? Whatever it says on the wall placard for maximum occupancy, you have to design for that. In reality, that many people hardly ever show up. If you do like a zone system with VAV, for example, it works similarly. You're putting a fixed amount of outside air on a central intake louver, and then you have all these individual zones that are modulating more or less, which means the right amount of ventilation air is not getting to the right space because they're modulating based on how much cooling they want, not modulating based on how much ventilation air they need. So it's pretty much uncontrolled in those scenarios. So what we're going to do as an alternative with demand control ventilation is, instead of just controlling the space based on temperature, we'll control the space based on temperature and ventilation. Now, in this case, it's a zone system, so I have temperature/ventilation sensors all over the place. If it was one big central area, then you might have only one system, right? So let's say this was serving a high school gymnasium. I don't need zoning inside a high school gymnasium. It's one air handler, one gym, I'm done. So I'd have one sensor on the wall that does temperature and ventilation, and that would be it. But if it's an office building, I'm going to have more of them scattered about. So if I can measure the actual ventilation effectiveness in each room, I can then decide if I have too little, i.e. bring in more ventilation, too much, bring in less ventilation or just the right amount, right? So that's kind of the goal, is get the right amount of air into the right room at the right time when that room needs it. So this is something that is allowable by code. You're actually allowed to go below the code required amount of ventilation air in the table if you do a demand system. And generally speaking, that demand system for most places, offices, retail, schools, etc., banks, will be CO2-based, carbon dioxide. The reason we use carbon dioxide is because carbon dioxide is what people are exhaling. You're breathing that out. And the major indoor pollutant in buildings is the people themselves. The more people in a space, the worse the air quality gets. So the more people that are there, the more fresh air I need. The less people are there, the less fresh air I would need. CO2 level does not tell you if the air quality is good or bad. CO2 level tells you how many people are breathing in the space. And then we're making the assumption that the more people breathing, the more overall pollutants there are. The more germs, the more coughs, the more weird colognes that somebody's wearing, right? Those kind of things. CO2 itself is not bad. I know it sounds like it because in the news you're always hearing about, carbon dioxide reduction being a big thing and carbon dioxide, free carbon neutral systems. That's because it's affecting the protective layer of the earth. But this is not that scenario. This is the CO2 literally coming out of your own mouth, right? So it itself is not poisonous. People don't die from breathing CO2 unless you have so much CO2 that you don't have any room in the air for actual oxygen. That would be a problem, but that would be very difficult to get to that point. However, because it has a giant CO in the name of it, it gets confused with carbon monoxide all the time. So you guys that are engineers or designers and you're putting CO sensors on your plans for an office building, and we're looking at this building going, why? What's going on here? You don't have a furnace in that room, or you don't have a boiler in that room. What are you doing? You got a rooftop outside. It's carbon dioxide, CO2, and that's what we're going to measure, and that is not a deadly gas. Indoor levels, a common indoor level that you would see, 800, 1,000, 1,200 parts per million is kind of the normal range. When you start getting above that, it becomes problematic as far as overall air quality goes. Outdoor levels are pretty constant. I know this slide says 400. That's kind of like a national average. When I take readings in the Chicagoland area, it's more like 475, 500. There's more CO2 in the air here than there is in Montana or something like that, right? Official national ratings are taken, like I think it's on the top of some mountain in Hawaii, which is probably got really bad data this month, but normally that's where it's done. And CO2 levels stay pretty much constant every single day. They don't change. Over decades they change, but not day to day. So people are breathing out a certain amount of CO2. A certain amount of fresh air is coming in the building to dilute that down. Since the amount coming in with the fresh air is a constant parts per million, it's pretty easy to do a mass balance equation within software tools to calculate where you're at there. The more active people are, the more they breathe, and the more they breathe, the more CO2 they exhale. So what does that mean? That means if you're doing a project that's like a gymnasium or a fitness place, that's going to be a different kind of math we're going to do. Not a different kind, but a different math problem we're going to solve than someone working in an office building. Office building, you're stationary, you're not breathing as much CO2 in there. So we'll do some different multipliers and stuff for like heavy exercise places. But other than that, let's say you're working in an office building, the amount of CO2 in the room is a function of how many people are in the room. If you got 10 people, you have a certain amount of CO2. If you double it to 20 people, you'll have double the amount of CO2. So essentially, CO2 can be used to count the people in the room. Then as you open up the outside air louver or close it down, it changes that. It is it's a slow enough reacting system that we can control it, but it's fast enough that we're not going to have any issues. So to give you an example, if I was around that 17 CFM per person range, somewhere between the yellow and the red line, this is time on the bottom. This is parts per million here from a room that was unoccupied, so 400 and some parts per million in space, just like a conference room, I think this was. People start coming into the conference room, and somewhere around 30, 45 minutes, we would be leveling off between these two lines. If I had a really underventilated space, it would take 2, 3, 4 hours to level off. Obviously, you wouldn't want that. And if it was an overventilated space, it would even out, in minutes. We want to be somewhere in this range here. So what's this going to look like? If we go back to our little bank, where's my mouse not working? Play nice. All right. It's designed for 25 people, so you got to bring 500 CFM in. You design it that way, you build it that way. The air handler can handle that amount. But then what happens in real life, we go back down to 5 people in there because the ventilation sensor, the CO2 sensor on the wall said, hey, you don't got this many people. You have a lot less people here. We can start throttling the outside air intake back. So instead of 500 down to 100 in this case. In this case, one person, 20. Now, in reality, we won't go that low because there's other reasons to bring outside air in other than just dilution of the indoor space. Specifically, you might have to have, maybe there's a bathroom there that has a little, 100 CFM exhaust fan. So now I have to have 100 CFM of outside air to make up that 100 CFM exhaust running on the fan when the fan's occupied. So I would not be able to go in that example below 120. I can go from 500 down to 120 because I got to take care of that bath fan. So there are things like that that come into play as well. So you got some limitations on that. Why are we allowed to do this? ASHRAE 62.1, which is the international standard for indoor air quality, and that gets almost cut and paste into the International Mechanical Code, and to a lesser degree into the Chicago Ventilation Code. It's a little bit different in Chicago, but it's similar. Those things all feed into each other. And that determines that we're allowed by mechanical code to go below the code required amount of outside air when the space is less occupied if we have a way to track that. And specifically, demand controlled ventilation is spelled out in ASHRAE as a method of calculating that, with CO2 sensors being the method to do that. You can come up with another way, but CO2 is specifically approved. A different way, you'd have to get an exception approval to do it that way. Like, for example, you could pay someone to stand at the door of the classroom, counting kids and marking them off on a clipboard. Oh, only 20 of the 28 kids came today, and you could turn a dial on the wall to throttle that back. And then little Johnny comes in late, you check him off on the list, and you turn the dial again to count for Johnny. You could technically do that, but it would be expensive to pay someone to do that when you get a couple $100 for a CO2 sensor instead. I won't read all of these to you, but International Mechanical Code has the same kind of language as ASHRAE. And then Chicago Ventilation Code, believe it or not, the year before ASHRAE, Chicago actually adopted the ability to do this. So Chicago is actually more progressive. I know we like to pick on Chicago and the code cycle here, but in this example, we are on year 20 of CO2-based demand control ventilation being allowed. The big difference from Chicago to, say, the suburbs, right? So if you're doing Peoples Gas, you're in Chicago. If you're North Shore Gas, you're in the suburbs. The big difference there is the set point of the CO2 sensor. In Chicago, because it's old school and they did it before the national standards, they were a little more conservative. So you have to use a set point of 1,000 parts per million. Everywhere else in the country, you don't do that. And what you do is use a set point that is 700 parts per million above the outside air level. So if it's 450 outside, your indoor set point becomes 1150 in that example, which saves a little bit more energy. But Chicago was a little more conservative when they came up with it. The energy codes. So the mechanical codes, all the mechanical codes for everybody on this call allows demand control ventilation. The energy codes, in many cases, now require it. So that's ASHRAE 90.1, or here in Illinois, you guys probably know we use the International Energy Conservation Code. We are on the 2018 version for the entire state, except the city of Chicago, which has early adopted the 2021 version. But both of those, as well as prior versions, will require CO2-based demand control ventilation for certain spaces. What kind of spaces? Densely occupied spaces. We'll go through a couple examples of that, but it's like movie theaters, gymnasiums, conference rooms. You got a lot of people and a small amount of square footage, you're required to use one of these sensors. So specifically, if you are in the 2018 Illinois code, 25 people per 1,000 square feet. If you have that ratio in your design for a certain area of the building, you're required to do this. If you are in the city of Chicago, which has just adopted the newer 2021 code, the new ratio is 15 people per 1,000 square foot. So my slide will be slightly outdated in that regard once the rest of the state catches up. But it was 40. At the exact moment in time, for most people, it's 25. And if you're starting to design buildings that are going to be built in Chicago, it's 15, and the rest of the state will catch up to that 15. 15 people per 1,000 square feet is not super dense, so start taking into account like regular offices and stuff like that too. All right, so the goal here is to ventilate for the actual occupancy instead of the assumed occupancy. This is more important than ever because there's lots of buildings now, because of the work from home movement, recently. There are a lot of buildings that are not fully occupied anymore. So why the hell are we bringing in ventilation for everybody when everybody's not there? So this has become more important type of thing. And that helps us stop overventilating. So if you didn't realize it, as we throttle back the amount of ventilation air coming into a building, let's say it's wintertime and I'm bringing in 10-degree outside air on some, regular cold Chicago day, I have to pay to heat that 10-degree air up to a more comfortable temperature to be used into the space. I can't dump 10 degrees on people, right? So if I bring in less of that 10-degree air, I don't buy as much gas to heat that up, right? Or in the summertime, the opposite, I don't pay for as much electrical cooling to cool and dehumidify the air back down. So if I can throttle that ventilation air back for most of the year, it'll save me energy. Now, for those of you that are familiar with economizers, right? Economizers are a free cooling device. Hey, it's cool out. Like today's perfect time, right? Hey, it's 60 degrees outside. Why am I running a compressor? Let's just open a window. Well, we don't have windows in most buildings, so we open up a louver in the outside air handler and bring in more cool air from outside. If you're doing demand ventilation, that does not change that. If there's free cooling available because it's cool outside and your building wants cooling, that will take priority over reducing the ventilation air. Because in that case, I'm not bringing extra ventilation air in because of IAQ reasons. I'm bringing it in because it's free cold air. So free cold air will take a priority over that. So the sequences on these controllers will do both of these. And by sequences on the controllers, I mean pretty much every single standard rooftop with an economizer that you've purchased in the past 15 years has the ability to do this out of the box. You just have to add the CO2 sensor. If you have a custom air handler or something like that, that's slightly different, but it still has the ability. It's just a little more work to get it done. But a rooftop, it's literally, there's 2 terminals on the rooftop that are waiting for a CO2 sensor to be wired to them. It's built in, it's standard, right? All the major economizer manufacturers, Honeywell, Siemens, Johnson, everybody has that built in. And then saving money, obviously, is the main goal for most people, right? If you can lower the bill, that's nice. It's great to save energy just, for good community reasons, but saving money on your bill is really nice. If we take an example here, make sure I'm good on time. We are. Take an example here. And if you guys have questions, man, you can just type them in, and I'll try to pay attention to them. And if not, I'm sure Glenn will see them and just interrupt me and say, hey, Ryan. So if you got a question, type it in. I like questions, so ask whatever you want. There's a little question box on GoToMeeting you can type in there. So this is showing you real data measured from a real building, and it's pathetic, but I've been using this same data from this building for like 20 years when I explain this to people. But there's more data. I'll show you some of that too. But this one, I just happen to like it. In any case, this chart goes from midnight to midnight on the bottom, and then up the vertical axis is ventilation air. So the top of it being your design ventilation air. Your air handler can probably do way up here somewhere, right? Based on the economizer sequence and so forth. But this is how much ventilation air you're supposed to be bringing in for your particular building. And then purple is the actual ventilation that happens when I put a demand system in. So green is a standard building, and then purple is blue once that same building was retrofitted. So normally, I think this says 7 a.m. or whatever it is, 8 a.m., whatever that says, the building goes occupied. The ventilation goes to its code required minimum position, ventilates at that rate the entire day. And then whatever this is, 6 p.m., it goes ahead and it shuts back off, right? That's a normal building. When I put a CO2 sensor in and track the actual occupancy and ventilate based on that, I follow this purple line, right? Because not everybody came to work on time, right? Somebody came late, just the way it is. They had to drop their kid off at school, they had a dentist appointment, blah, 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 blah. Then people cut out early for lunch. This is the people leaving for lunch, by the way. So these people are gone for lunch. These people stay and eat lunch at work. Most of them come back from lunch, not everybody. Some don't bother. And then at 3:30, they check out to go golfing, pick their kid up from school, and whatever else it is that they're doing. Hardly ever is it actually fully occupied. So you can take advantage of that and only ventilate for who's there in purple, and everything between purple and the top of that green line is gas and electrical savings for your outside air treatment. There's numerous studies. This is a federal study. This was one building on the left over here. This is hundreds of buildings on the right. Every office building pretty much has what we call the 2-hump profile. Every single time it's like this. People leave for lunch, right? Everybody doesn't come back in the afternoon. People leave early every time. You got a restaurant, you get a 3-hump profile, as you might expect, breakfast, lunch, dinner. These are very predictable patterns. If you got an office building with 2 people working there, okay, this is not your pattern because most of the time both of you are there. But if you get a decent amount of people, 20, 30, 50, 100 people, the chance of everyone coming to work is pretty much zero. So other than offices, which are good candidates for this, right? And you can see in an office, here's my top designed ventilation rate, and here's my annual average ventilation rate once I put a demand system in. So instead of ventilating 100% during all the occupied hours, on average, I'm ventilating 70, whatever this is, 73%, we'll call it, right? There's some days I'm up here in the 90s. There's other days I'm down here in the 50s, but on average, it was 73%. Once again, this is off of real buildings. Retail, similar, but much more dramatic. It's like a 90% reduction in the amount of ventilation air that I need because the retail space is designed for some, big crowded day, some, Black Friday sale type day. But then the rest of the year, it's not Black Friday. The place is not that packed. So there's plenty of times that you're barely occupied, right? You're down here in this single digit percents in terms of occupancy in the retail store. Restaurants, similar thing. It's designed for some kind of Saturday night, 7:30 p.m. dinner crowd. And then you think about it on Tuesday at 11 a.m., it's not super crowded. So there's lots of times the restaurant can throttle back. You have to be a little bit careful with restaurants because sometimes restaurants are poorly designed, we'll say, from an HVAC standpoint, and they're using the dining room airflow as a bad way of making makeup air for the exhaust hood in the kitchen. And if you're doing that, you can't throttle back the dining room airflow too much because you'll starve off the exhaust fan in the kitchen. But assuming they've done a good job from a pressure standpoint and separated the kitchen and the dining room into two separate airflow zones, then you can definitely do this ventilation strategy in the dining room area. And there's different strategies that you can use unrelated to CO2 in a kitchen. And in schools, I find this one to be the most interesting because in schools, well, for starters, a lot of schools don't have full occupancy or even any occupancy in the summer sometimes. So you can save a lot there by throttling those back. But then during the year, there's tons of savings as well, right? So maybe your classroom's designed for 26 kids, but your classroom only has 23 in there this year. That's 3 kids all year long I don't have to ventilate for. Doesn't sound like much, but it's 3 kids times X CFM per person times X amount of hours for the whole year. And then additionally, what about the kids that don't come? You got 23 of the 26 kids that the room is being assigned to, but any given day, you may have 19, 20, 21 of them because a couple of them are sick, they're not there, they went on vacation, whatever. The biggest thing, other than summer and not using the room fully, the biggest thing though is like if you think about your kids' elementary school or whatever, they're in their classroom doing their thing, and then at 10:15 they go outside for recess. No one's in the classroom. Why am I ventilating it? I don't need to. Then they come back in, but then immediately they go over to the art room, and once again, no one's in the classroom. There's all these chunks throughout the day that nobody's in a given room. Every room is designed for full maximum occupancy. But all the kids at that school can only be in one room at a time, right? They can't put themselves in all 6 of their classrooms at the same time. So some schools, especially elementary, have these large time blocks of rooms being unoccupied. This just shows you some national averages on payback scenarios for different kinds of things. It's always fast. I mean, it's always measured in months, not years for CO2 paybacks. It's pretty quick. And there's federal studies that back all that kind of stuff up as well. These were the really early adopters back in the 90s, people that were jumping on way early. But now, I mean, it's literally tens of thousands of buildings that do this. More early adopters on there. All right, so how's this actually going to work from a functional standpoint? When you decide how far you can throttle back the outside air, things you have to think about, what's the code required amount of air to begin with? You got to think of the pressurization. So I mentioned that in that bank example. Some of your fresh air coming into that bank might also be needed as the makeup air for the toilet exhaust. You got the little individual bathroom sitting in that bank lobby with the one toilet stall and the one little 100 CFM fan. I can't go below that amount because then my building will go to negative pressure, which for most buildings, I don't want that. So in addition to the codes for ventilation air, you also have to think about what things are going to be removing air from your space, i.e. exhaust fans, and make sure I don't go below that amount of CFM on my intake when I modulate it. Do you have any requirements other than the code that are driving ventilation? Like maybe the building has some specific like lab spaces or something like that. You just have to start thinking about those kind of things. But for most places, you don't have that scenario. What kind of buildings make sense? We've been using this chart forever, like literally forever. I started here in the 90s and we had this chart then. So that's how old this is. It's a little outdated. I always joke that I'm going to update it, but I'm lazy, so I'm literally not going to do that. But we used to give this to like all of our sales guides and stuff too. A, B, C. So A means it's a great application for CO2-based demand control and ventilation. C means it's a horrific application. Do not do it. You will probably get us sued. Don't do that one. B meant it's a maybe. Why don't you come talk to me? We'll go through some details. We'll figure out if it's going to work for this building or not. So examples of A, like I mentioned, a classroom. No brainer there. We explained that one already, right? Auditoriums, movie theaters. That's like literally the best candidate is a movie theater or an auditorium. It's used for X amount of hours a day, and then it's just vacant for large amounts of time. Anytime you have a lot of people coming and then emptiness, that's going to be a really great candidate for this. If you have a lot of people and they're there constantly all the time, no matter what, that's not a good candidate, right? I need people to be coming and going for this to make sense. Then I have something to modulate. Any type of indoor sporting venue, same reason as a movie theater, right? You got some, gymnasium, you got a 4,000 seat college basketball stadium or whatever, and it's packed, obviously, because the team's really good, but then the team sucks and no one's there, right? So coming and going, large amounts of people. Office buildings, we explained. Retail, like the little bank thing, those are good candidates. We usually stay away from the medical stuff because there's all kinds of pressurization rules at hospitals, but general areas, lobbies, waiting rooms, cafeterias, physical therapy areas, we can mess with those ones and not affect the building pressurization topic. But other stuff like an ICU, we're probably not going to mess with that. Hotels are really good candidates, especially the conference and meeting areas, because they, just like a movie theater, they have a lot of people there for some wedding on a Saturday and, 200 people. And that same space may have 20 people there for a business meeting on Monday. And then on Tuesday, there's nothing in there. So those are really good candidates. Gymnasiums, as we mentioned, game rooms, ice rinks, bowling alleys, all that kind of stuff. The ones that are bad are typically ones where either the occupancy does not change no matter what, so hence there's nothing to modulate, or the ventilation rate is being dictated by something other than human being occupancy. So for example, guard station at a prison, it's kind of got to be occupied. It's not like they take some time off and no one's there. It's 24/7, the same number of people in that station, always. So there's nothing to modulate. A 911 call center at the village hall, it's always occupied. Someone has to be there. There's no reason to try to modulate it because the people have to come, right? Other places that would be no-nos would be ones that would be like where the ventilation is driven by non-people things. So a dry cleaner. The reason why there's so much ventilation in a dry cleaner is not because the two people working in the back room, it's because of all the chemicals used. You got to dilute those down. So whether it's two guys or one guy that show up for work that day, it's the same amount of chemicals. So we're not going to modulate that kind of stuff. Locker rooms and pet shops, they already smell horrific. Do not cut back the ventilation rate. It's not going to help you in that regard. The odors are already horrible in those kind of places. Kitchens, I mentioned, we do demand ventilation in those. It's just not CO2 based. It's a different technology that basically infrared, count the burners that are on, adjust the ventilation, exhaust accordingly. Parking garage, the same thing. We do demand ventilation in those. It's not CO2 based. For parking garages, or even like loading docks and stuff, it would be CO, carbon monoxide, because that's what the cars are kicking out, or NO2, nitrogen dioxide, because that's the diesel trucks are kicking out. But it would not be CO2. That's why it's a no-no on this list. Anything regulated by the FDA, probably not going to mess with it. Anything regulated by IDPH, probably not going to mess with it. Swimming pool, chlorine is driving that, not the number of people, so we're not going to mess with it. And then B's were the maybes, right? So let's get a maybe. A beauty or barber salon, right? Let's say it's like a nail salon, right? Some of those nail salons, not that I go there because you can tell my hands are hideous. The nail salons have these little mini exhaust fans right at the workstation that exhaust outside. If they have those, then you can go ahead and make adjustments to the ventilation rate for the main space. But if it's not, and the whole room is just basically polluted with nail paint chemicals, you're not going to mess with the ventilation rate in those kind of places. So that's how some of these end up on the maybe list, right? That's probably enough for that. Let's see. We do have a question. I thought we had a question.
Yeah, I got a couple questions. You seeing those, Ryan?
I see one here from, it's like cut off though. Tom. Okay, let's see what it says.
Weiser.
What about dialysis facility? I don't know exactly what a dialysis facility is. So
that's where they're on. They get an IV in them and they get their blood cleaned. They're sitting in a chair. You know what I mean? They're sitting. There'd be a whole bunch of people in there doing that at one time.
Most of those places would probably end up being okay. So if you looked on this magical chart over here, that would fall under like this patient room category. If that space is being used for multiple things, then it would be a problem. But usually the places we're avoiding are pressurization rule spaces. So like operating rooms are a big no-no. Everything has to be like leaking out of the operating room, not leaking into the operating room. So it has to stay positive pressure. But what you're describing for that dialysis facility sounds like it probably would be okay, because it's probably doesn't have anything weird going on. It sounds like it's a regular patient type room.
The other question, Ryan, was doctor's office, and I'm assuming that's kind of like a regular office.
Yeah, so that would be this on this category up here, this patient room, be the same thing as that dialysis discussion. As long as just a regular doctor's office where you're not doing anything weird, you're not doing like any surgeries or anything like that. But there are some doctor's offices that have a surgery suite. The surgery suite, you're not going to mess with that room, like outpatient surgery suite. You're not going to mess with that one, but the lobby you would, the general hallway areas, and even the patient rooms you could do this in.
And then there's one more question. It says, what is the base ventilation rate?
All right, so I don't know if I put that slide in here. I'll pull that up as we're talking. But I didn't think I put. Yeah, I didn't do that. I'll do that. I'll pull it up while we're talking. So the ventilation rate is going to be specific to your code, right? And it's going to be specific to the occupied space that you're in. So for argument's sake, since we're ahead of schedule slightly here, I will pull up the code because there's nothing more fun than in a live class reading the code book. Books, codes. We'll do the International Mechanical Code for right now. So when you pull up the code book, and most places other than the city of Chicago exactly are following this exact table I'm about to show you. I'll explain the city of Chicago in a second. It's slightly different. All right, so if I go to ventilation section, and I'll just scroll through till I get to the code table. All right, so here I am. We'll just use something at the beginning of this just to make it clean. Let me put this up on the screen. Okay, you guys should be able to see that wonderful code book here. So this is the way it works for everywhere, pretty much everywhere in the whole country except the exact city of Chicago, city boundaries, and the state of Wisconsin. For some reason, those two places are unique. But the suburbs of Chicago and everywhere else in the country pretty much is like this. So you look at this table here, what you're going to do, and this is everything in the past 15 years, you're going to add this column right here. I'll do it this way. You're going to add this column to this column. So this is the number of people in your space multiplied by this number. And then this is the amount of square footage multiplied by this number. So if we go to a traditional example, say like an office building, right? So for an office building, let's just say it's the office area, I need 5 CFM for every person in that space. We'll make the math easy and say it's 100 people. I need 500 CFM of outside air for those people. And then I need 0.06 CFM for each square foot. 0.06, let's say it's 10,000. Once again, to make the math easy, that's 600. So I need 500 and 600. I add it together. That space needs 1,100 CFM of outside air. The code allows me to modulate this part, the 5, the people part. I cannot modulate the square footage part because that's not going to change. It's not like my walls start moving and shrinking, right? The reason why we have a people and a square footage part, specifically the reason why this got divided in 2004, was to allow for demand control ventilation. So we can modulate the one without having to worry about the other. And the reason we have the two things is because people give off a certain amount of pollutants, and then the building itself gives off a certain amount of pollutants. Whatever varnish I have on this desk, whatever that wall over there was painted with, right? Those things all have VOCs and chemicals and stuff like that. I need to dilute those down, and the people. The people change, the building doesn't, realistically. So I can modulate the people part. So in this case, I would have 500 plus 600 in my example. That would be 1,100. I can modulate on the CO2 sensor from 1,100 down to 600 if people don't show up, right? If I had something different, like say a classroom, let's say it's a classroom for little kids, instead of 5 and 0.06, I have 10 and 0.12. I literally have double the amount of outside air required for an elementary school classroom compared to a commercial office building. But I can modulate those things, right? So what ends up happening when you set this up, assuming whoever sets this up sets it up correctly, which is always, a nice big assumption, they got to do this math, right? So they get those ventilation rates. By the way, okay, so City of Chicago, I said I would mention that too. City of Chicago still has a weird ventilation code. If anybody in the city is listening in, I no longer apologize for saying that. It's really weird. So in the city of Chicago, the code does not tell you how much outside air to bring into a space like every other code in the country. It tells you how much supply air to bring into space, total supply air. And then in the code, it says 1/3 of that supply air needs to come from the outdoors. The problem with that is normally the supply air is dictated by my load calculation. And in the city of Chicago, your load calculation has nothing to do with your code required supply air. So it doesn't yield to good dehumidification control and things like that because of that. So it's kind of a weird way to do it. It's just really old school because Chicago code is so much older than everywhere else, almost everywhere else. They had set it up their way and they've been kind of riding it that way for decades. So hopefully one day they follow the rest of the code. So it's a little bit different there. As a result of that, and as a result of those tables being really outdated in Chicago compared to the load calcs, City of Chicago ends up yielding the absolute highest ventilation rate requirements in the whole country. There's nowhere that people have to spend more money on heating and cooling ventilation air than in the city of Chicago. Because of that, CO2-based demand control ventilation has the absolute fastest paybacks in the city of Chicago. I mean, you could pay this thing back in a couple months. It's that fast. In contrast, if you're logging in from Wisconsin, hey, thanks for joining us today. We appreciate you guys, Wisconsin Dells, and all those good things you give us, fireworks, fantastic cheese. Wisconsin has the absolute lowest ventilation rate in the country. So it has the slowest payback for CO2 control because the ventilation rate's already really low. But Chicago, it has the fastest payback. And in the suburbs and the rest of the country, it's a normal payback, if you will. So what I'm going to do when I control this thing is I'm going to modulate the system between the design ventilation rate and then my new minimum rate. My new minimum is whatever that square footage number came out to. In my example, I made the math easy, so it wasn't really a realistic ratio, but I said it was going to be 600 square feet, or sorry, 10,000 square feet, 600 CFM for the building, and another 500 for the people, right? So in my case, it would have been up here is my design ventilation rate, and down here had been my lower modulation rate for just the building. In this case, it was a higher density of people than my example, so the ventilation rate has 80% worth of modulation. The air handler is not moving this amount of CFM through the fan. The air handler is moving something way, way up here, right? So the air handler fan can do this. And this percentage of it was coming from the outside. So it says 100%. It's not 100% of the CFM of the fan. It's 100% of the code required outside air. The fan could do this because there's going to be recirculation air as well. So this is my code number I would have put in, and I can modulate that. In this case, I'll just follow this curve right here. I can modulate it as the amount of people actually changes. And all of this area in green, I don't know why I'm shading an area that's already shaded. It's because this pointer's cool. That area in green becomes the amount of outside air I don't have to pay to heat. I don't have to pay to cool anymore. But I need this base rate here, which is going to be the higher of the per square footage number of my code, or the amount of air I need to use as makeup air for general exhaust and bathroom exhaust that I have to run anyway.
Hey, Ryan,
Yes, sir.
is the base ventilation assuming the supply fan is on 100% of the time?
All right, so for commercial buildings, everywhere we have a commercial building ventilation code, which is pretty much everywhere, you have to run the fan whenever the building's occupied. For you guys that are putting in residential thermostats on the wall and telling the fan to run in auto mode, you are in no way complying with the code. It's not been code for decades. It's been wrong for so long. You have to run the fan constantly. You have to, unrelated to this demand ventilation, you have to run the fan constantly during all occupied hours. And then you're required by energy, that's per the mechanical codes, you're required by the energy codes to stop running the fan constantly when it's unoccupied hours. So for every building, you have to define when it's occupied and unoccupied, right? So 7 a.m. to 6 p.m., the office building is open, occupied hours, I have to run the fan. I have to bring the ventilation air in. Then from 6 p.m. in that example to 7 a.m., it's unoccupied. I don't run the fan. I don't run the outside air damper. I'm required to shut the fan off, and I'm required to shut the outside air damper completely. Even if the air handler kicks on just to do like some general heating in the middle of the night, the ventilation damper still needs to stay shut. And if you have like a cleaning crew that comes in, that does not count as occupied. That's a temporary transient occupant, and that's not an occupied occupant. It sounds weird I said occupant twice or 5 times. Hopefully that made sense. So yeah, your fan will be running constantly in these examples. But even if you didn't buy the CO2 sensor, your fan should be running constantly. To give you an idea of like the parts per million kind of thresholds, I said the city of Chicago, 1,000 parts per million is your automatic code required set point. In the suburbs, it's the outside air plus 700 parts per million. And if the outside is usually 450-ish around here, you end up with 1150 as your set point. So here would be like the suburbs, and here would be the city of Chicago. City of Chicago is a little more conservative, i.e. less energy savings in that regard. But the city of Chicago already has freakishly high ventilation rates compared to everywhere. So you're more than making that up in the payback scenario. If you get to spaces that you see, like you're walking around with a handheld meter and you're measuring these things, and I do that sometimes, and you start seeing spaces that are up in these ranges, they're not really well ventilated. I mean, no one's going to be dying because it's 1,600 parts per million, but it's not really great, right? It's not a health hazard. It's a productivity problem. The lower the CO2, the worse the CO2 rate is, the higher the CO2 rate, the less productive people are. You're getting a slightly lower amount of oxygen than you otherwise would, right? So from like a human productivity awesomeness, I'm going to, compete in this Olympic event. I'd rather be down over here, right? But I don't want to pay for all that outside air either. So that's why we kind of got this, ideal range in the middle over here, where it's a good balance of costs and human productivity. If you start getting really high, then it starts becoming a health hazard. Not because the CO2 itself is going to harm you, right? It's coming out of your own mouth. It's not going to harm you. But because you have so much CO2, you've deprived the space of having enough oxygen in the room, right? So really tight buildings that are poorly ventilated will fall into those categories. Old leaky buildings fall down over here somewhere. Once again, as there's more questions, go ahead and throw them out there. I'm going to skip this one because nobody does that anymore. It's old school and stupid. We do it this way now. So instead of turning on, we used to just, I guess I have to explain the next one. We used to throttle the damper, like, oh, the CO2 is high, open the damper back up. Oh, it's low, lower it back down. Open, close, open, close. Not a very good way to control it. Now we modulate the damper. So we give it a range. If you remember, I said that, that's 700 above the outside air level. In this case, it was 400 outside for this chart. So 1100 is my indoor set point, right? That becomes my high end of the range, and I set a low end of the range. So I don't wait for it to get to be 1100 before I start modulating the damper back open. As it creeps up, I modulate the damper. And as it goes down, I modulate the damper. I just constantly modulate the outside air intake damper so I don't have to slam it open, slam it close. It's more of a smooth thing. It's kind of like driving your car, right? Imagine you only had a gas pedal that was on and off, right? You can either do 80 miles an hour or 0. That's the only options you have, nothing in between, right? So you hit the gas, fly to the next stoplight, slam on the brake. You're like a teenager, right? It's not very energy efficient. It's not very enjoyable. It's not very, well, it's enjoyable, I guess, with a car, right? But it's not a very productive way to use your car, and a lot of wear and tear and all of that. Same kind of thing here. I'd rather have it be smoother modulation. I'd rather be that dude that's coasting to the red light to try to maximize his gas savings and that kind of thing. So we're going to modulate these things now. Normal economizer controllers will do it this way as well. And if you're doing a building automation system, you'll be using a PID loop to modulate it, but same kind of idea. How fast am I getting to set point? Let me react to that as opposed to just waiting till the last minute. I should also mention on any of these charts, no matter which one we're looking at, like even this one, at no point in time is the CO2 sensor going to take me from here, design ventilation, up to there. I'm never, if I set it up correctly, I'm never going to bring in more outside air than I would have if I didn't buy a CO2 system. Don't think of it as your damper opening more because your CO2 is high. It doesn't do that. I mean, it does, but it doesn't do that. Think of it as your CO2 level drops, we close your damper a little bit. So you start out with the code required amount, and if everybody doesn't show up to work, hence they don't breathe CO2 out of their mouths, we can start throttling back because they didn't come. Many people set it up wrong, and they set it up to do this direction, and that wastes energy. It's a huge problem in the technician knowledge gap, and they set it up, and you're doing this thing to save energy, and for the first couple months you're wasting energy until someone figures out you set it up backwards. So it's kind of a problem. As far as CO2 sensors go, if it's an open space, one big room with an air handler, like a school gymnasium, typically one CO2 sensor will do the job. One CO2 sensor can cover, depending on the manufacturer of the sensor, most of them will tell you can cover about 5,000 square feet, right? So if you had 10,000 square feet, you probably should get 2 CO2 sensors, right? Otherwise, the one, by the time it senses it, it takes a long time for that air to move across the room. If it's a space where it's not open, right, and you have, like, say, VAV dampers and stuff like that, and zoning dampers, and you got air going to this room and not that room and then this room, then you really need to put a sensor in each of the spaces. What you cannot do on a room or a space like that is you cannot put it in the return duct. There are applications when you can. A dampered system is not one of those systems. So if you had an open area, once again, the high school gymnasium, and you don't want to put the sensor on the wall because it's going to get smashed by a dodgeball anyway, sure, you can go ahead and put it up in the return duct and sample that way, right? But you cannot do that on a dampered zoning system in an office area because that return is going to give you an average of all of the rooms. Well, I don't want to know the average. I want to know what's happening in each room because some rooms will be peaking and be underventilated and other ones will be unoccupied. So we put a CO2 sensor on every VAV box controller, and we track which ones need more, and we open up those zone dampers more. And then what we do is control the main outside air damper to the worst, i.e. the highest CO2 sensor reading. And if I'm satisfying that one, obviously I'm satisfying the other ones. So for zone systems, you put a sensor in every room, CO2 sensor in every room. For non-zone systems, you could put it in the return duct. Additionally, I would say only put it in the return duct if there is an open area. So once again, high school gymnasium, I look up at the ceiling, I see the air handler right there, no problem. You go into Menards or Home Depot, you look up, you see the air handler, yeah, return duct, no problem. If it's a ducted return above a drop ceiling, don't use a duct return air sensor because that's not going to give you just the return air, it's going to give you all the leakage associated with that ductwork. If you're in Menards, there is no ductwork. There's like 2 feet of duct. There's no duct leakage, right? So if you're in an area that has long return ducts, don't use a return-mounted CO2 sensor. Use a space wall-mounted one. If there's any questions on those locations, let me know. Like I said, economizer controllers have this built in. You literally just have to buy the sensor and then wire it up, right? The sensor's a few $100s, right? Depends on what quality of sensor you want. And then wiring it up is labor. So once again, depends on your labor rates. But this could be something as cheap as, $400 or $500 install cost. It could be $700, $800 install cost, depending on where you got to run this wire and how hard it is to get to. I'm in a building right now with a drop ceiling, and the air handler is literally up 10 feet and over 12 feet. It'd be pretty easy for me to run a couple more wires, right? But in another building, it might be like this beautiful architectural wood engraved ceiling thing. I'm not cutting that open, so it's going to be harder in that space to do it, obviously. But it's built into all the economizer controls. Every current model of economizer control has it, and pretty much any economizer controller for 15 years has it. And if your rooftop's more than 15 years old, you shouldn't be adding stuff to it anyway. You probably need to replace the rooftop. It's probably highly inefficient as it is. Get a ComEd rebate to replace that thing. If you got a building automation system, you can obviously add it to that as well. It's a little bit different because now you got to have somebody program it, whereas an economizer is already factory programmed to do this. You got to have somebody write a little bit of code for it, but it's not like it's writing it from scratch. I mean, the building automation guys have done it hundreds of times, so it's not like they just cut and paste the code from a different project. So in addition to the sensors already being ready for the economizer to go in, the ability of adding economizer is an option. So older systems before economizers were widely code required would have just had a 2-position damper. And either it would be motorized, so it means it opened during occupied hours and it closed during non-occupied hours, or it'd be manually positioned where somebody positioned it and locked it and left it there, and it's just always open all the time. If you add an economizer to that, you can add a CO2 sensor along with that. Once again, don't add an economizer and a CO2 sensor to a 15-year-old unit. It's past its life expectancy or at the very end of its life expectancy. Don't put any investment into that system. But you got one that's like 5, 6, 7 years old, and you're going to keep it another 10 years. Yeah, you might want to add an economizer and a CO2 to that one. Honeywell's I'm not picking brands here, but that's just like 90% of the market is Honeywell for economizer controllers. That's why I have this on here. This Jade controller is the only one that's currently manufactured other than some special OEM replacement stuff. So this one's CO2 ready, no problem at all. Even this other one that you can still get in certain scenarios for replacement, it is CO2 sensor ready. And then these older ones are not. But at this point, you're probably not running into any of those. If you're using the new Siemens economizer controller, it is CO2 ready. And then if you're using, building automation from Train, Carrier, Johnson, whatever, those guys can all do it too, obviously. All right, this is old school stuff. Are we on time? I probably got to get this done in the next 5 minutes here, right? CO2 sensors are 100-year-old concept. It's just that CO2 sensors used to be really expensive, so you couldn't use them for controlling a regular building. Now that they're a few $100s, you can do that. But it's been in the engineering handbooks for 100 years, right? Becoming significantly more popular in 2004, where my chart ends, because that's when, other than the city of Chicago, that's when all the other codes finally said you can do this. Before that, it wasn't prohibited. I started in the late 90s, and we were doing this. It wasn't prohibited by code, but it wasn't spelled out that you could do it either. You were kind of having to negotiate every time on it with the inspectors. But then in 2004, it became like a codified thing. In Chicago, 2003. Why is it more popular now? It's allowed by mechanical codes explicitly. It's required by energy codes for many types of spaces. And the cost of the sensors, due to significantly more manufacturing volume, has gone down and down and down. And once again, this is like 20-year-old as well. So now the cost is probably more like here to buy a sensor, right? It's gone back up a little, but it's not like it was when I started and it was, $1,200. The sensors are, most manufacturers, I think actually, I want to say all, but it's hard to say all. Most manufacturers no longer allow you to field calibrate their commercial grade sensors. Industrial ones you can, but that's a different category. They no longer allow you to field calibrate because everyone was calibrating it wrong. So instead, they are now self-calibrating, which sounds weird, which basically works like this. As long as the building goes unoccupied for 4 hours a week, it can self-calibrate, because the outdoor CO2 levels don't change at all throughout the course of the day, weeks, months. I mean, on decades level, they change, but on a daily basis, they don't. So the outside levels don't change, and buildings are leaky enough that over the course of 4 hours of no one being there, all of the human-produced CO2 has been exchanged through the building envelope walls with the outdoors, and now the indoor and outdoor CO2 levels match. So every night when it goes unoccupied, it can basically just calibrate itself back to that original baseline, right? Here is 3 sensors sitting side by side for like a week, eventually tweaking themselves to read the same level as each other, even though they don't know each other exist. It's just happening naturally by calibrating to the outdoor level. Well, that's not good. Hopefully you guys can still hear me. My PowerPoint said no dice. It just closed for no apparent reason, which is always annoying. Is there any other?
Yeah, we can still hear you. Yeah.
Is there any other questions while I open it for the last 2 slides here? Anybody type anything in? Want to talk about your deep feelings or anything like that? Good, because I don't have feelings, so that's good. This is always a good sign when PowerPoint's like, nah, we don't want to open. All right, well, maybe I won't reopen that. One last chance. Kill it. Open it again. Cross my fingers. Do a little rain dance. There we go. This is going to work this time. All right, and go back to the last slide. Same sensors over 3 years, calibrating themselves to each other. So the summary is you want to ventilate for who's actually there versus who is supposed to be there. That prevents you having to pay to heat, cool, dehumidify, sometimes humidify, filter any incoming air that you don't necessarily need. And it's allowed by all the mechanical codes, all of them. And it's required by many of the energy codes. Required by all the energy codes, but for many types of spaces. So it's got pretty big paybacks. Once again, as a reminder, on the Peoples and North Shore gas side, 5 cents per square foot, as long as you don't have a system that has zone reheat coils, because those are cooling only systems by definition. So anything else is fair game. And then you add that to the 4 cents per square foot you get from ComEd, which overlaps with pretty much all the Peoples and North Shore territory, and you get a total of 9 cents per square foot. I wish you guys could figure out a way to make it an even 10 cents so I could do all the math in my head. All right, any other pending questions that we did not address? Glenn mentioned that next month, I'll pull that up again real quick, has a topic of the boiler as well as furnace and rooftop tune-up submissions. So if you didn't know, you can get rebates for doing tune-ups on existing equipment, and you can do that every so many years for the same building. So log in on September 27th so you can learn how that works and see what offerings you've been missing out on to offer your end user clients. What else we got, Glenn?
That's about it. Do you have your contact information in case somebody wants to get a hold of you?
Yeah, hit me up.
There it is.
I just put my cell phone number on.
Right.
I stopped doing that because I teach class literally
No,
every
I get it.
day. So I'm not going to call
Email's
people back until 5 o'clock anyway. So, but send me a note. We can always schedule a call or something too. And then that way, if you want to talk about something regarding.
Wait, you call people back at 5 o'clock? You don't call me till like 8 or 9.
I usually call you back a couple of days later. I usually wait.
Well, that's
Make
usually
sure you
sometimes
really,
midnight.
really needed something.
No, I appreciate it. Thanks again for, let me see here. Change presenter. All right. Let me see. Do I have my info? Where did it go? I lost it.
I believe it's 8675309.
Yeah, 8675. There you go. Okay, there it is. All right. Who are you gonna call? Get a hold of me. It's my cell phone. You can call my cell phone. I won't call you back at midnight. I'm not as busy as Ryan is, of course. And you can see my email there. And that, do not go to that website. That website is wrong, I now see. So, let's see. All right. Yeah, please visit this website here, Trade Allied Center. Why does it keep coming? There it is. TradeAlliedCenter.com. If you have any questions, please feel free to get a hold of me. Thanks again for attending. Ryan, thanks. Did a great job as usual. And we look forward to seeing you guys next month, September 27th, for boiler tune-ups and how to process those. That'll be done by Kevin McKay, one of our energy advisors. He'll walk you through step by step. And if you have any questions, like I said, please get a hold of me or Ryan, and have a great rest of your day. Thanks again.
Awesome. Thanks, Glenn.